So this is gonna be my new YouTube channel. If you notice what this says, if it's backwards in the camera. So that's my new YouTube channel that I am hoping to get online. Search it up if you search it up and I'll tell you on a meeting, a class meeting.
So Michael, what do you want to talk to your friends about today?
My dad will be helping me.
Okay, what do you want to talk to your friends about? I
want to talk to you about wormholes, but first I'll have to explain space-time and dimensions, space-time, dimensions, and I'll give a little thing about dimensions at the end.
Okay. So
wormholes and black holes too.
First.
So a zero-dimensional shape is something like a dot. But one-dimensional shape is something like a line.
Why? What makes it one-dimensional?
Because it only has one dimension. A dimension is where something like a dot extends out into one length. Two-dimensional shapes are like circles, triangles, and rectangles. But my favorite will be three-dimensional shapes are like cylinder, cubes, rectangular prisms, triangular prisms, spheres, pyramids, and cones. But my favorite three-dimensional shape is, actually, we don't know if it's three-dimensional, dodecahedron. I don't know how to pronounce it.
Dodecahedron.
It has 12 sides on it. It's like a really it's like a 12-dimensional shape.
Now, Michael, you wanted to tell them, now that they know about 3 dimensions, tell them a little bit about what the 4th dimension could be.
It could be maybe like our dimension in 3 makes us another. I have the perfect way to explain that, but before that, but while this, I will be explaining. Let's go see what it could be.
Okay, so explain to them what this is right here. What is
space-time?
Okay.
Make sure.
It's a part of physics where we explain gravity.
Okay. So this blanket is what?
So this blanket is space-time. Heavier objects curve it down, but it doesn't matter how big it is, like the sun. It matters how heavy it is and how much mass it has.
Okay.
And
so what do these things here represent? These little balls?
These little things explain the gravity.
And they're sitting on time, right?
Yeah, these are like planets, stars, planets, maybe medium planets.
Okay. Okay, so now, why don't you show them what something very, very big and massive would do to time?
So, planets are so far away, they're not even doing this.
So what happened? What did that massive
This
thing
big planet has enough. This big planet can like curve it enough. And look, space-time can also curve to another one. That's what makes it go.
So, do you remember, explain to them what this big, massive thing did. What did it do to time?
It went to time.
Did it bend it?
Yeah, bend in time. Black holes, which I'm going to explain now.
Michael, where'd you go?
Okay.
This will be perfect to explain it. So a black hole, I know this isn't so heavy, but black holes infinitely curve space-time down. It looks like it's infinite, but soon it comes down to a point. A very small point, about 1 Planck, or is it Planck? Planck, which is the smallest measurement in the universe itself, which think of is pretty crazy. But the singularity squashes everything into it. Even if it's, I don't know, like smaller black hole would rip you to shreds for me, and I will talk about the many parts of a black hole. So, you can see there's the inner event horizon. Right here is singular. They did the outer event horizon is not here, and the ergosphere is actually on the outside. So this is the singularity, which I was just talking about. Infinitely squashes things. But then after that is the inner event horizon. Nothing can escape that. The outer event horizon, well, it's about the outer event horizon is, well, I don't know, well, a little bit less gravity. And then on the ergosphere is the last part of a black hole. So the ergosphere spins things. Faster, you need to go faster than 1 to 100 times faster than the speed of light to get to
Now, Michael, can you show us what we don't know is on the other side of a black hole, but what we think could be on the other side, like dark matter, that maybe would have the opposite effect? Can you show us how that would look in space?
So it would be like this.
It might push things away.
Yeah, mostly just push things out of sight.
Okay.
So we think that this may not exist. It's just a theory.
Okay, now let's go back to the table and show them the last thing about wormholes you wanted to teach, now that they know about space-time.
This is what I was really hoping to teach about. This thing will take about, it's like Wormholes, my favorite things.
Okay.
So, if this is home, this is my house, and this is school.
I can see it if you bend it.
And this is 5 to 10 minutes, and talking about reality. 5 to 10 minutes in real, yes, 5 to 10 minutes. But my bus doesn't have to do that if there's a wormhole between them.
This is space-time.
This is space-time.
So, you're gonna bend it, right?
So if we could get a wormhole to bend it, we could probably just, I don't know, make some touch. So the bus won't have to do that hour wait thing to there. But it could make my sensor. Now, let me show you something. A little something here.
Okay, good. That's it. Okay.
Well, there's.
So tell them that's a wormhole.
Yes, a wormhole.
And now school and home are what?
Are, like, you can travel there faster than the speed of light. Light is the fastest thing in the universe. But I have one thing to tell you. We think that it could make dangerous destruction. My house, maybe Florida, like kilometers away, even other planets kilometers away, could probably get pulled in because all it is a spinning black hole, which I will show you a picture of a wormhole. Like, we can't actually see them, so I just did this. The space-time sheet is really just like this, kind of.
And that's the bending of space-time?
Yeah, but you could go from the Earth, go down the wormhole to the faraway galaxy. Maybe the Andromeda galaxy that's heading towards the Milky Way. You could use that to save the Earth if it does collide.
Okay, good job. Okay, say and that's all.
That's all.